When we study a wave, we can usually focus on what's happening with the peaks in the wave. Watching the peaks can give us the wave's speed, period, and wavelength. In this code, we'll use rings to represent a sound wave's peaks. We keep track of these rings in a list called wave, since the wave is made up of peaks represented by the rings. Each of these rings begins centered around the red speaker with the same radius. Then, in the loop, we increase the radius of each ring. When one period of the wave has passed, we create a new ring, since a new peak is ready to go out from the speaker, and we reset the time since the last ring was created. By increasing the radius of each ring and creating new rings, we make a series of peaks that travel out from the speaker at the same speed in all directions. Because they all start from the same starting point, they form concentric circles that keep getting wider. This animation accurately depicts how sound waves travel out from a speaker or water waves in a pond. Now comes the interesting part. Suppose we move the speaker to the right at a steady velocity. Because the speaker is in a different place every time it emits a peak, the rings are no longer concentric. They get squished together ahead of the speaker, and they get stretched apart behind the speaker. So, our green listener receives a wave with a higher frequency when the speaker is moving toward her, and she experiences a wave with a lower frequency when the speaker is moving away from her. This is why you hear a change in pitch when an ambulance passes by. The sound waves are literally being compressed and stretched. We call this compressing and stretching of the sound waves the Doppler effect. The Doppler effect becomes stronger if we increase the speed of the speaker. The wave peaks become more squished and more stretched. In fact, if you make the speaker move at exactly the same speed as the sound waves, you can see all the peaks combining at the front of the speaker. This shape is called a Mach cone and is responsible for the sonic boom that occurs whenever an aircraft breaks the sound barrier. The Doppler effect also happens when the listener is moving. Even if the speaker is stationary, the listener will experience a different wave frequency when heading toward the speaker than she will when moving away from the speaker. And of course, the Doppler effect happens in full force when the speaker and listener are both moving. In fact, if the speaker and listener are moving at the same velocity, the Doppler effect is canceled out entirely and the listener experiences the original frequency of the wave. The Doppler effect makes for some really interesting physics, and you can learn more about this behavior by completing the activities at the link in the description below.